All right, in this video, I'm going to try to talk through this pentagonal number problem. Before I start, let's get this out of the way. This problem was too hard. I probably shouldn't have assigned it. I looked at it in the book and was like, oh, okay, you add these up, you find some pattern, they realize the pattern, they express the pattern, get the answer, good enough. Well, it turns out the pattern's a little bit more complicated than anything we had seen in class, so it was kind of an unfair question. So what I'm going to do is this homework problem, I think anyone who kind of tried it and put forth some effort got at least 2 out of 4 on it. So I'm going to make this problem just out of 2. And so if you got 3 out of 4 on this problem, not only did you get 100% on the problem, but you got extra credit for this problem. And hopefully everyone feels like that's fair. And in the future, I'm just going to try to assign problems that are a little bit more fair, stuff that everyone can do. All right, so that being said, let me give this a try. So the first thing you're supposed to do in this problem is kind of just make this chart and start counting dots. So they already pictured for you what I think they gave you the first 4 pentagonal numbers. Get on the right page here. And you just went around and counted the dots. You counted 1 dot and then 5 dots, 12, and then 22. And so the first question that it asks you is to complete this table. And so really you can just count dots for all of them except for 5. And for 5, if you draw kind of the next shape and just go and count dots carefully, I think you'd end up with 35. Fine, good enough. So far, I think it's a fair problem. A little bit annoying, counting dots, but whatever, fair enough. But then it gets a little bit, I don't know, unfair. So I guess this right here would just be part A. And for part B, it says, make a sketch to represent the 5th pentagonal number. Fine, I did that. How many dots will be in the 9th pentagonal number? So this is where it gets a little bit tricky. One way to do it, 6, 7, 8, 9. It's just by drawing a lot more dots. It'll take a while. I mean, this is already pretty ugly. You can tell it's hard to draw on a computer, so I don't want to just draw more dots and count them. Another option would be to kind of start looking for a pattern. So if you're looking for a pattern, I think a lot of you guys saw this pattern. You might have noticed that here, this 5, I mean, just sort of the way these are written, the way I counted that there are 35 in the 5th pentagonal number is not by counting all the dots. It was by counting the blue dots and knowing that I already had 22 in red. So I counted 13 blue dots, and I was like, all right, 22 plus 13 is 35. So if you saw the numbers that way, you might have thought about this 5 right here as rather than it's just 5, it's 1, what I had before, plus 4 more. There's this 1, and then these 4 that were new at that stage. And then this 12 right here was the 1 and the 4, this 1 and then this 4, and then the ones that were new at that stage, 1, 2, 3, 4, 5, 6, 7. Oops, 1 plus 4 plus 7. And then using that same logic, you might have found that 22 is 1 plus 4 plus 7 plus 10. And 35 is 1 plus 4 plus 7 plus 10 plus 13. And you might notice that we got some patterns going on here. It looks like we're adding 3 each time. So I could jump all the way down here to 9 and know that 9 would be 1 plus 4 plus 7 plus 10 plus 13 plus 16 plus 19. Let's see, how many do I want here? Well, for 5, I was adding up 5 numbers. So for 9, I should be adding up 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stick those all into a calculator, add them up. You'll get the number right here, which will be our 9th pentagonal number. I don't really want to add them right now, so we'll get this answer before this video is up. But for now, maybe that would make sense to people for how you get the 9th. And you're like, yeah, that works great, except for part D, it asks me for, I guess it asks me if there's a pentagonal number with 200 dots. Fine, that's kind of an annoying question, but you can do that. If you add this number up, I think it's pretty close to 200, a little bit below. And then maybe you're like, well, the next one would be just like this, except for adding 28. And maybe if you add 28, now you're above 200, or add a couple more. At some point, you realize that now it jumps over 200. D, no, it doesn't really work. I don't think that's the part people had trouble with. I think it's E where people really didn't like it. Find a formula for the number of dots in the nth pentagonal number. So using this pattern we saw up here, you might be able to figure out sort of an idea of what it would look like. It would be 1 plus 4 plus 7 plus 10 plus 13. Add 3 each time until you had n terms. But how do you write that as a formula? Well, a couple options. What you could do is note that this is 2 less than 3, this is 2 less than 6, this is 2 less than 9, this is 2 less than 12. What I'm saying is that each of these numbers is 2 less than 3 times the order that appears in this sum right here. So for the formula for the nth, what we'd have would be, it would be 1 plus 4 plus 7 plus something until we got up to the nth term. But I think we could figure out what the nth term would be, because the first term is 1, the second term is 4, third is 7. It's always just n times 3 minus 2. In other words, 3n minus 2 here. So a formula for the nth would be this thing right here. If you gave that, I think that's fine, to tell you the truth. I think this is a perfectly good answer. You can actually take this a step further. I think some of you that looked this up online found a more closed form, something that didn't have this dot, dot, dot. And the way you could do that, actually Gauss's method will work. So maybe you remember from Gauss's method that if you're trying to add up the numbers, let's say 1 to 99, you can do it by writing up the sum you want, 1 through 99, and then below it writing that sum again sort of in a backwards order. Maybe I'll write or Gauss method. So if I wanted to know what these things all added up to, I could say, well, it's 1 plus 4 plus 7 plus, and then my last one would be 3n minus 2. And so this right here is my answer. But if I wrote these backwards, 3n minus 2, 3 times n minus 1 minus 2, or 3n minus 5, 3n minus 8, and so on, all the way until you got a 1 right here. And what you'll see is when you add up every single column, you get the exact same number. When you add up each column, 1 plus 3n minus 2 is just 3n minus 1. Same thing if you added this column, this column, this column, and so on. So really all I have to do is figure out what do I get when I add up a whole bunch of 3n minus 1s. And if I could figure that out, that would be twice my answer. Well, how many of these 3n minus 1s do I have? Remember, there's exactly n terms up here, just like there was 9 terms in this sum. For the nth number, there would be n terms. So I have n different columns, and each column sums to 3n minus 1. And that product right there is twice my answer. So what's my answer? Well, one way you could write it would be n times 3n minus 1 divided by 2. I think some of you that looked it up online might have found something slightly different. Take this n and distribute it through and get 3n squared minus n divided by 2. And that's totally fine too. In fact, now that we have this answer right here, we might be able to understand. I mean, maybe there's definitely other patterns going on in here. If we stare at these long enough, we can probably figure out what other patterns live in these numbers. But rather than do that, well, should I do that? No, I don't want to do that. Maybe now that we have 2 different formulas for the answer, you might be able to go back, look back if we're using the 4-step process, and figure out maybe there's a different way that would have gotten us straight to this answer. That makes a little bit more sense. Maybe it's a little bit more logical than Gauss's method. But this is one method that you could use. Again, it's a little bit beyond what I want you to be able to do in this class, but this would work. Before I end this video, I just want to make one more little point. Another way that you could do it is sort of breaking these down a little bit. So instead of thinking of the 5th pentagonal number as 1 plus 4 plus 7 plus 10 plus 13, if you instead think about it as, I got this 1, I got this 2, I got this 3, I got this 4, and I got this 5. And granted, that's not all of the dots, but that gets rid of a lot of them. So what I'm saying is for the 5th pentagonal number here, instead of viewing it like this, we could have said, well, it's 1 plus 2 plus 3 plus 4 plus 5. That stuff I just circled in green. Plus, you have some symmetry going on here, right? The amount left over on this side is the same as the amount left over on this side. So plus twice what I have left over on each side. Well, I kind of have a 0 left over in this top one, and then a 1 left over right there, and then a 2 left over right here, and a 3 left over right here, and a 4 left over right here. And since I have the exact same amount on this side, I can take care of those just by putting a 2 out in front. So really, instead of viewing this as 35, I could have viewed it as this sum right here. Would that be easier? Well, I don't know. I mean, then when we got down here to the nth, this is a lot easier to count up. This is all the numbers from 1 to n. And we can add up this sum using Gauss's method. And then these we can add up too, plus 2 times 0 plus 1 plus 2. Careful here, you wouldn't go all the way up to n, because in the fifth number I only went up to 4. Right, I started with 0 and then 1 and then 2. So we'd actually go all the way up to n minus 1. I can add up this sum using Gauss's method. I can add up this sum using Gauss's method and then double it. And then if I sum all those together, you should get the exact same answer as we figured out down here. So really some options in terms of how you do that. I don't know what's easiest for people to see. I just figured I'd kind of talk about this problem. In case I haven't said this 10 times, a little bit beyond what I want you to be able to do in this class. If you can look at this and make some sense out of it, if you can use Gauss's method when it's 1 plus 2 plus 3, that's what I want from this class. But I didn't just want to leave this one without a solution, so there's a video talking about it. Sorry if I droned on and on and on. I will stop this thing here.